The design for the Xenith T-Series began in 2006, 2 years prior to when it was introduced. So it was about 1.5 to 2 years in development. The key design features of the Xenith T-Series are, of course, number one, the windshield fork. We had seen a special design brake that we thought could be enclosed inside the fork, thereby moving the brake from the front of the bike, creating drag, to the rear of the fork and shrouding the fork around it, improving the aerodynamic characteristics of the leading edge of the bike.
It sounds simple enough, but taking a really aerodynamically ugly piece of alloy away from the front of the bike and attaching it more rearward would automatically make the product more aerodynamic.
Secondly, we were one of the first manufacturers to move the rear brake, which is traditionally mounted on the seat stay, underneath the chainstay, thereby moving it out of the wind. Also, during the computer modeling process, we worked extremely hard with the shape of the tubes. Instead of using what people consider a traditional arrow tube shape, where you have a leading edge and the tubing goes straight back to the point, we worked with the tubing shape to make it more of a radius bend back to the point, more of a wing shape to make it more aerodynamic, not only from a frontal direction, but also when you get at angles of 5, 10, 15 degrees, the frame is more aerodynamic at those angles. That tubing shape carried through not only on the down tube, but also the seat tube, the seat stays, and also our own carbon seat post. When we brought our first prototypes to the San Diego low-speed wind tunnel, we wanted to confirm what our computer models were telling us. First, we tested the frame and fork as a unit to see how aerodynamic, and actually we were very excited how the windshield fork would perform. During that initial test, the drag figures were so low that the wind tunnel engineers thought something was wrong with the wind tunnel. They shut the wind tunnel down, recalibrated the platter, and started to test over again, and the drag figures came up again very low, lowest they'd ever seen for a complete bicycle. So we knew we had something with the windshield fork. We tested it 0 degree, 5 degree, 10 degree, and 15 degrees at 30 miles an hour. They had never seen wind drag figures this low for a complete bike before in that wind tunnel, and they've tested with all the leading competitors.
We wouldn't be where we are today with the Xenith T-Series program if it weren't for the San Diego low-speed wind tunnel. That staff there has over 125 years combined experience in wind tunnel testing. I'm not talking about 125 years of aerospace engineering, mechanical engineering. They have 125 years combined experience in wind tunnel testing. Frame development in 2007 and in 2008 was driven largely by drag data. We maxed, or felt that we had maximized everything that we could with that data. Research into how we could better utilize the wind tunnel to take the 2010 Xenith T-Series platform to the next level led us into flow visualization techniques. There were 3 visualization techniques available to us. One was smoke, one was something called tufts, the third technique was French chalk. To get specific about what these are, smoke, a white pillar of smoke introduced into the air chamber, and it simulates airflow around and over the product. Tufts, which is a piece of yarn that's either taped to the product or is held on a wand near the product, will show airflow near the surface of the product. But it was the French chalk procedure that was absolutely the most informative for us. David Sambor, the chief engineer in charge of the aero test team, told us that no one in the bike industry had ever used French chalk before. He was surprised that we had actually made the inquiry and said during our testing that we wanted to use it. It's rather messy. It's a mixture of kerosene and oil and talc that's poured over the frame at the same time that the wind tunnel is being geared up. It being a liquid, it's pushed across the frame. It having talc in it will allow it to be visualized and recorded. And it being a liquid, being blown, means that it'll dry. When that chalk dries, we can take that frame that shows the vortexes and the uneven movements of the liquid being pushed by the air over the frame. We can take that to manufacturing and modify our our shapes by hand so that we can then go back and repeat it again. So we've got digital recordings of that material being moved on the surface of the frame, and it doesn't get any more illuminating than what is happening on the surface of the frames. You want to keep that flow attached to the surface of the product. It's when it becomes separated that it creates turbulence. It's when it becomes separated that it increases drag. So in both our research and in performing the actual test, to see this progression from over to near to on was incredibly informative and totally drove the design of the 2010 Xenith T-Series. Keeping in mind that before that, it had been solely drag data driven. 2010 separated from, not to use the word separation again, but separates itself from our own platforms. And we think from the rest of the industry by taking flow visualization to the ultimate and using a technique that had not been used in the bike industry before.